Alright, so today we're going to be dealing with linear inequalities in two variables. So we've done examples so far in class where we're like x is greater than 5. So that's a linear inequality in one variable. And if you remember graphing this, we would have to plot it on a number chart. We would count out 5, and then we would do an open circle because it's greater than 5 and not greater than or equals to. And then we would shade one half of this number line to indicate that for all values greater than 5, that is going to be a correct solution for what we're dealing with. So when we're talking about linear inequalities in two variables, essentially what we're going to end up doing is we're going to be graphing a linear line on our xy axis, and then instead of shading one half of a straight line, we're going to be shading one half of this function that we have graphed on our xy axis. So why don't we deal with the example? Well, let's graph 2x minus 3y is less than or equal to 6. And this is written in a standard form so that way we can deal with both of our axes, the intercepts of our x and y intercept. So when x equals 0, we can compute our y-intercept. So when x equals 0, we're going to have the equation minus 3y is less than or equal to 6. We divide both sides by negative 3. Remember, we're going to have to flip the inequality. So we're going to get y is greater than or equal to negative 2. And if we want to think about graphing that on our xy plane, we're going to count down to the y-intercept of negative 2. 1, 2. Y is greater than or equal to negative 2, so we're going to have a full circle. And if y is greater than or equal to negative 2, we're going to shade the upper half. Alright, so when y equals 0, we're going to get the equation 2x is less than or equal to 6. And that implies that x is less than or equal to 3. So 1, 2, 3. We're going to shade in a full circle. And we know that x is less than or equal to 3. So we're going to shade to the left of that. Alright, so now that we have plotted both our y and x axis, we can then draw a line, straight line that passes through both points. And how do we determine which side we're going to shade? Well, we just shade the side that we have already indicated is going to get shaded. So two directions that our arrows have been pointing. And that will be graphing all of the solutions to the equation 2x minus 3y equals to negative 6. So we could take some sample points, like the point 1, 1. That is supposedly in our solution set that we have indicated by shading in this region. And if we plug in the point 1, 1 into our original equation, we're going to get 2 times 1 minus 3 times 1. Is that less than or equal to 6? So we're going to get 2 minus 3 is less than or equal to 6, or we're going to get negative 1 is less than or equal to negative 6. And that's correct. So all the points, that's what we're trying to do, all the points in this shaded region are all solutions to this linear inequality that we have right here. So that's what we're doing. When we draw the linear line and then shade in one half of the graph, we are indicating that all points in the shaded region, and including the line we drew, are points that yield a correct statement for 2x minus 3y is less than or equal to 6. Alright, so that's one way that we can graph this. Note that if it was slightly different, if we just had if 2x minus 3y is less than 6, so instead of less than or equal to 6, if we just had 2x minus 3y is less than 6, so we're still going to have the same y-intercept of, what was it, negative 2, and the same x-intercept of positive 3, but instead of a solid line that passes through these 2 points, we can do this with a dotted line that passes through these 2 points. And we're going to shade in the same half of the graph. So now we are indicating that all points in the shaded region up to, but not included the line, is going to be solution points to our linear inequality. So that's how we deal with when it's just less than or greater than with no and or equals to part, is that we draw a dotted line. So the difference between these two, not just graphically, we draw a solid line versus just a dotted line. And what's that indicating is that on the solid line graph, that all the points that are on this line are also solutions to our linear inequality. Whereas here, all the points on the dotted line are not solutions to our inequality. So that's what it means when we're doing that inequality symbol right there. Alright, so let's do another example. We've done a couple of examples of dealing with concerts, and you have different prices of tickets. And let's assume that you are a concert promoter. And we have two different types of tickets. Tickets A, tickets B. Tickets A cost $125. Tickets B cost $175. And let's say that we want to generate a revenue of at least $700,000. We need revenue of at least $700,000. Alright, and now we're going to have to draw a linear inequality that represents the solution set. So we're going to have 125 times the number of A tickets that we sell, plus 175 times the number of B tickets that we sell, and it has to at least be $700,000. So it's going to have to be greater than or equal to $700,000. So that is our linear inequality. Now we're going to be asked to graph that. So if let's graph. We have our A-axis and we have our B-axis. So if B equals 0, then 125A has to be greater than or equal to 700,000, or A is going to have to be greater than or equal to $5,600. So we can plot that. 5,600, and we got a solid dot, and we're going to shade the upper region. Alright, if A equals 0 to find that B-axis area, we know that 175B has to be greater than or equal to 700,000, or that tells us that B has to be greater than or equal to 4,000. So we do a solid circle, and we're going to shade to the right of that, because B has to be greater than or equal to 400,000. And we can draw a straight line in between these 2 points, and we're going to shade the upper region that we have indicated with this upwards arrow and that arrow to the right. So that means we're going to shade in this region. Now note, in this example, we've only dealt with the first quadrant of our solution set. We didn't bother graphing across the entire graph. We only dealt with the first quadrant of our solution set. And that is because we're dealing with a real world example of it. Is that, hey, this is the equation that we got. Now note, we can't sell negative B tickets, and we can't sell negative A tickets. We can only sell 0 or a positive number of both types of tickets. So we're only going to be dealing with the first quadrant of our graph. So that is why our solution set is a little bit more like a smaller area than dealing with the entire all possible x and negatives and positive of x and negative and positive of y. Here we're dealing with only positive values of b and positive values of a. So that's how we can graph that. Alright, so let's do another example. A company produces foam mattresses in 2 sizes, regular and king size. It takes 5 minutes to cut foam mattresses for regular mattresses and 6 minutes for king mattresses. If the cutting department of our business only has 50 labor hours available each day, how many regular and king mattresses can we cut in one day? So this is a linear inequality problem. Note that it takes 5 times R would be the total number of hours that we devote towards cutting regular mattresses, because it takes 5 hours per regular mattress, plus 6 minutes for each king mattress. So 6 times the number of king mattresses is going to be indicating the total number of minutes that we have for cutting king size mattresses. And now note we have 50 labor hours per day. So we have to figure, so these are in minute terms, 5 minutes for regular mattress, 6 minutes for king mattress. We have to figure out how many minutes are available in a day. So 50 times 60 equals what? 300,000? That sounds about right. 300,000 minutes. Has to be less than or equal to 3,000 minutes. And that's the linear inequality that we have written. Note that we have 5 times R is the total number of minutes that we devote towards cutting regular mattresses. 6 times K is the total number of minutes that we devote towards cutting king-size mattresses. And it has to, at the end of the day, we have to devote less than 3,000 minutes towards cutting both regular and king mattresses. So let's solve this. So let's graph this. So if R, let's pull out this. So we got our king size mattresses and our R mattresses. So if R equals 0, then we have 6K is less than or equal to 3,000, or K has to be less than or equal to 6,000 divided, or 3,000 divided by 6. We're going to get what? 500 minutes. So K has to be less than or equal to 500. If K equals 0, then we're going to get the equation 5R is less than or equal to 3,000, or R is less than or equal to 600. So R has to be less than or equal to 600. We can draw a solid line in between these two. And then we're going to shade in the region that is underneath the curve. So this shaded region, including our line, is all of the available points that are part of our solution set. Alright, so that does it for today's lesson.